Welcome to the great final of the first day of Photonics Days 2022. We have the award ceremony of the Applied Photonics Award 2022. We heard 2 different keynotes and had 4 lectures in this morning who show that the applications of photonics are very, very broad. There are so many different topics, branches, industries, and that leads us to the award because we also have a lot of different topics here. The Applied Photonics Award is a Young Researcher Award awarded by Fraunhofer IOF, and we're very pleased that it will be presented by Dr. Robert Kammel from Strategy and Communications at Fraunhofer and Professor Michel Hers, who you met before. But first I want to hand the word over to Dr. Robert Kammel to present the award.
Thank you very much for the introduction. And so as we have seen today in the keynote talks, photonics is a very broadband and colorful area of science and also application. And for us at Fraunhofer IOF, it's very important to both support young people with their education and scientific progress, but also with the application of scientific ideas, in particular in photonics, for applications and the transfer into applications for science, industry, and society. And for this reason, we have announced the Applied Photonics Award several years ago and now continue to reach this out every year. And with this award, we try to support young students for their master's thesis, PhD thesis, and bachelor thesis in the field of photonics, in particular when they focus on certain applications. And so it has become a tradition that you can reach out this award here during the Photonic Days in Jena. And in particular, in this year, I'm very glad and thankful that we can realize this event here in person today, on the one hand, and that again we have had several great applications. And so at first I want to thank all the applicants who had reached in their theses, but also for the jury who had the difficult task to select the winners. Moreover, I want to thank all the supporters of these events, which is on the one hand the Association of German Engineers, the VDI, but also the companies Active Fiber Systems, Trumpf and Jenoptik. And with this, let's move on to the actual award ceremony. I'm very pleased to present this award here today with one of our excellent keynote speakers, Michel Hers, who would like to, I think, provide the first award winner.
Thank you so much, Dr. Kammel. It's really always been actually not just a goal of mine, but also a heartfelt wish of mine to engage with young people. And so this young scientist award for me is something very particular and very special. So it's a great pleasure for me to present this year's winner, or winners, of the Applied Photonics Awards, together with all of you here, who can then celebrate the success of your peers. We'll start with the first category, and that is Best Bachelor Thesis. The award for the Best Bachelor Thesis in 2020 goes to Magdalena Hilbert for her work on gas sensing with 2D materials on exposed core fibers. I will read from justification of the jury. The jury praises the holistic approach of the thesis as well as the applicability of the measurements. For this reason, Mrs. Hilbert is awarded the Applied Photonics Award. Congratulations, Mrs. Hilbert. We look forward to learning more about your work in your presentation. The stage is now yours.
So obviously now it's my turn to present my bachelor thesis quickly with the topic gas sensing with 2D materials on exposed core fibers. Okay, yes. So we start now with the principal sketch. As you can see in the middle, there are triangles, and those represent the 2D materials. They are placed on top of a fiber and on top of the exposed core fiber. The laser beam is guided directly inside the fiber core and interacts with the 2D material, which has before interacted with the surrounding molecules of the atmosphere around the fiber. The spectrum can be detected later and analyzed. So the advantages are that the detection can be made immediately and therefore has a low time constant. Because the spectrum can be analyzed later and another place, the remote sensing is easily possible. So my task was to investigate experimentally how the photoluminescence changes as a function of different gas concentrations. Here you can see the cross-section of the fiber, and the fibers made by fused silica. In the middle you can see the fiber core, and it's directly in touch with the exposed side. So the fiber core touches at one side the environment directly and can interact with the gas molecules there. As you can see here on the figure, the 2D materials are placed directly on the fiber core. And the laser beam interacts, or the guided mode interacts with the 2D materials, and the PL mesh is sent into the fiber mode and can be collected later. Possible fields of application are, for example, atmospheric research or chemistry laboratory. Actually, everywhere where observing specific gas concentration is needed. But why 2D materials? 2D materials are molecularly thin, therefore they have a really high surface to volume ratio. And yeah, just to name some characteristic of the semiconducting light-emitting 2D materials, they have a tunable band structure, large exciton binding energies, strong light-matter interaction, high carrier mobility, so they can a lot do. As you can see here, the gas molecules can be absorbed by the monolayer molybdenum disulfide. Molybdenum disulfide is one of the TMDs, one of the 2D materials. And when the gas molecules are absorbed by the monolayer surface, then there's a charge density difference. So it behaves like an electron donator or electron acceptor. Obviously, depending on the molecule that is adsorbed. So for different molecules, different gases, the molybdenum disulfide reacts differently, and that we can use. Here is the setup, the experimental setup. You can see a laser. You can see the coated fiber inside of a gas chamber. You can see the camera and the spectrometer. The camera to observe the guided modes. And yes, the function of the chamber is to set around the 2D coated ECF a controlled gas atmosphere. For example, we had one gas measurement we did. I will present only one here. With increasing molecule number of NH3 gas, the spectrum did change and had a redshift. As you can see in the figure on the left side, there was a redshift. With increasing number of NH3 molecules. And with increasing number of NH3 molecules, as you can see on the right side in the figure, the total PEL decreased. In summary, we can say, or I can say, first for MS2-coated ECF, trends of the PL change for different gas concentrations were measured. Secondly, MOS2-coated ECF is a possible platform to detect NH3 and N2 gas. And thirdly, presented contraction is applicable to other 2D materials and also to other waveguide systems to increase the application range of those sensing technologies that are fiber-based. A little outlook. My supervisor, Kuyet Ngo, just built a setup in a gas laboratory Ilmenau to determine the upper bound limit of sensing mechanism. So, thanks, and yes.
For your presentation and for the really great work, and we're very happy to present you with the prize.
Congratulations.
Congratulations. Herzlichen Glückwunsch.
Alles gut.
And now on to the next.
So this was the winner of our first award. So let's move on to the second one. The second is awarded for the best master thesis. This goes to Felix Wechsler and his work on the Kaleido microscope. And here the jury has underlined the impressively simple idea of improving the capabilities of classical optical microscopes and the promising application approaches. And moreover, this work was carried out in close cooperation with industry partners, which of course is in well scope with our award here. So I think we're all interested in how this microscope works. So congratulations at first, and we're happy to hear from you about your work.
Yeah, I'm preparing my 20 minutes talk now. Yeah. No, yeah, thanks a lot for the invitation, and for me it's a real honor being here today, and thanks a lot for giving me this award. And yeah, so let's go back, like 140 years ago, microscopes were looking like this, and there's a fundamental issue with those microscopes. So you prepare a thin slice of your object, and you place it under the microscope, and unfortunately, from a single view, so from a single look at the sample, you only see a 2D projection of a 3D model. So you're not able to retrieve 3D information from the sample. And to solve that problem, we invented the Kaleido microscope in the spirit of light field microscopes. And yeah, the key idea to the Kaleido microscope is actually a kaleidoscope. So I bet you all, when you were a child, you all had a kaleidoscope in your hand. And if you're looking through such a kaleidoscope, you see countless of replications of the scene. However, those are not countless replications of the same scene, but instead those are different views onto the same scene. And similar to the human stereo vision, different views mean that there are different aspects in the image, and from the slight difference in the images, you're actually able to obtain the 3D information. And yeah, so how do we build the Kaleido microscope? We actually place the kaleidoscope, so the mirror part, in front of the objective. So therefore, the Kaleido microscope. And what you can see here on the image, so the bluish thing, that's actually the mirror box. So it's in the size of a few millimeters, actually below millimeters. And we're also questioning, or I would be also interested to tackle the question, how we can manufacture such a kaleidoscope in a better way than we currently do. But yeah, that is in principle the key idea of the Kaleido microscope. So how does the replication work? So we now place our sample F just inside the mirror box. And by simple ray tracing, we see a center view. So an observer on the right-hand side would see basically the center view of the F. However, by tracing the rays, there's also, due to simple reflection, there is a copy on top of the center view, and there's also a copy below of it. And those are not copies, but instead, those are three different views, and from the differences, we are able to obtain the 3D information. And then the last step is simply to put that in front of a microscope. So to the more familiar people, that's the objective of the microscope, and that's the tube lens down there. And we can also see down here on the sensor, we have the 3 images of our sample. And also we can see a drawback already here, because given by Ernst Abbe, we know that the resolution of a microscope depends on the light cone. And as we can see in the aperture stop here, we have to share the light cone. Therefore, each of the views has a light cone, has a numerical aperture, which is by a factor of 3 smaller. Therefore, we lose lateral resolution. However, another part of our thesis was to investigate the behavior. What happens if we are not using parallel kaleidomicroscopes, but instead a tilted kaleidoscope, so a tilted mirror box. And in that case, we can see that we can break with the assumption that the light cones are divided by a factor of 3, because in this case, we can see that they start to overlap. So by using tilted kaleidoscopes instead of parallel ones, we are actually able to increase the 2D lateral resolution, and also we could show that also the 3D lateral, or basically the 3D resolution, is better while using the tilted kaleidomicroscope. And if we then image a sample, the raw images look like this, and you can see a lot of replications or a lot of symmetries in the picture. And that is due to the fact that if you look very closely, you can see here actually the borders of the mirrors. And therefore, we see here the different views captured in a single shot. And if we now extract the single shot, we can basically establish a reconstruction algorithm. And the reconstruction algorithm produces images like this. So this is supposed to be a 3D image. And the general idea is that we know how a microscope works. So we have our 3D sample in the image, in the object space, and then we physically model by a scalar wave model, so we include diffraction. So we physically model how the 3D volume maps onto several 2D images. And having our 2D images, we can try to solve the inverse problem. So we can do the other way around to recover our 3D volume. And this is how we do it, basically. So at the end, I really want to thank all my collaborators and especially my supervisors, so Professor Rainer Heinzmann from the Leibniz IPHD, actually right over there, and also Professor Ivo Urke from the Kalens Company, and also the Kalens Company supported me financially during this work. And last but not least, I want to thank the Julia language. So Julia is an open source language, and without all the open source contributors around the globe, we wouldn't have been able to establish this work. So in that spirit, thanks a lot. We are shaping the future, and I'm really looking forward to the talks of the next laureates.
So please don't run away.
So, congratulations.
Congratulations, impressive work, very interesting. Okay, now we've seen 2 very cool undergraduate theses, and I'm very excited now to move on to the next category, which is the award for best dissertation. It goes to Dr. René Kirbach. His dissertation is dedicated to, I'm quoting, the investigations on linear optical wireless front ends and application-free, sorry, that was too long. Investigations on linear optical wireless front ends and application-specific free-form lenses for optical wireless communication. You can see why I had to read that, right? It's a long title. With his work, Mr. Kirbach contributes to the development of new wireless communication networks, as the title indicates. These are necessary to ensure reliable data transfer in the future. The jury emphasizes that a complex topic between optics and electronics is considered here. Mr. Kirbach presents a functioning system and application with great innovative potential. This achievement is worth the Applied Photonics Award 2022 to the jury. I congratulate you, Mr. Kirbach, and now look forward to your presentation, where I hope you will elucidate us on the length of the title in particular.
One, two. Yeah. Thank you very much for the funny introduction. Now I have to find my presentation. First of all, I would like to thank the jury for awarding my work with this prize, and I would like to thank the sponsors for making this possible. And finally, I would also like to thank my family, friends, and colleagues who supported me during the PhD thesis. Now you had enough time to read the topic by yourself, and now I'm happy to give you a short insight into my work. If we have a look at mobile data traffic on global scale, on the left side, we see an increase from year to year, and it's nearly exponential. But there's more. The number of devices that use mobile communications is also increasing from year to year, and this is not caused by smartphones or other handheld devices. This increase is mainly coming from what we call machine-to-machine communication. This type of communication can typically be found in the context of Internet of Things, Industry 4.0, or automation in general. Now, the thing is that some applications have other demands for the communication infrastructure than past applications had. For instance, think about an automatic driving vehicle. It's fully clear that this vehicle needs a reliable communication channel, and information always has to arrive in time, otherwise the vehicle might crash. Now, the problem is current radio frequency technologies struggle from interference due to overlapping channels, and this is why they struggle to provide low latency reliable data transfer. This is one key motivator for the development of 5G technologies and future 6G technologies. The optical wireless communication is now an alternative technology which is based on using light for communication. Typically, the communication takes place in well-defined spots, and within this light spot, you can achieve high reliability and low latency data transfer. Now, the goal of my work was to investigate the potential of modern optical wireless communications, and maybe one unique thing about the work is that it's multidisciplinary, so it has an electronics part and an optics part. In the electronics part, I investigate on the potential of linear front ends, and in the optics part, I investigate the potential of freeform optics for certain applications. Now let's have a look at the electronics part. Here I was able to show that I can construct an optical wireless transceiver by using commercial near-infrared LEDs, and with these LEDs it's possible to achieve data rates of up to 1.55 gigabits per second. The transceiver is able to communicate in bidirectional way, and one really cool thing is it's fully plug-and-play into existing networks, so you could easily replace a cable or something like this. Another cool thing is that it's not only capable of point-to-point communication, but also of point-to-multipoint communication. This means you could place one transceiver at the ceiling, and this transceiver can handle multiple transceivers beneath it. Within the work, I can show that the transceiver benefits from several adaptive features. For instance, you could regulate the bias point of the LED in order to save power without losing data rate, if you do it in a smart way. Now let's have a look at the optics part. I developed a framework for the calculation of freeform surfaces. And I calculated a lot of design examples and was able to show that we can achieve higher efficiency, of course, higher range, and we can also address new application scenarios. Let me just highlight the last 2 points. For instance, you might have the idea using laser diodes instead of LEDs for communication because they are faster. The problem is typically laser safety and eye safety, and this limits your laser power. But there are ways around it. For instance, you can construct a freeform multipath lens. In this case, in this study, the lens enables us to increase the laser power by a factor of 20, and thereby we can increase the link range by a factor of 4.5, which is quite a lot. I also said we can address new application scenarios. Have a look at this free-form hybrid lens prototype. This hybrid lens consists out of a transmitter part shown in blue and a receiver part shown in green. And what it does is it achieves a nearly rotational symmetric optical arrangement. And we can use it for communicating in rotating scenarios. And we constructed a transceiver based on this principle. And the transceiver can be used to replace slip rings, which typically have a rather low lifetime or limited data rate. This approach is quite promising, so that we have a couple of industry projects with it. And one of our industry partners constructed a communication module based on the transceiver. And since February this year, actually a pair of those communication modules operate at the ISS. And since nobody complained yet, I guess they're still working. And with this being said, thank you for listening.
Thank you, Dr. Kilber, for the equally humorous presentation. That was fascinating, and congratulations on your awesome work. And you now receive your statue.
So,
is it a
congratulations.
Statue? Thank you. Herzlichen Glückwunsch. Sehr cool.
So, as I've said in the beginning, we have received a lot of outstanding applications, and so it was very difficult for our jury to select only 3 winners. And due to this, we have 2 additional jury prizes for their scientific excellence in this year. So, and therefore, it's a pleasure for me to introduce the first jury prize for scientific excellence, which goes to Jan Wilke Henke for his master's thesis on the demonstration of the interaction between free electrons and fiber-integrated photonic resonators. Here, the jury outlined that the excellence here was in the combination of integrated photonics and electron microscopy, which lays the foundation for a new class of hybrid quantum technology. And moreover, this work was also published in the well-renowned research journal Nature, which of course also is an honor. So, congratulations from our side.
Yes, so first of all, thanks for the very kind introduction, and also thanks a lot to the jury for, well, thinking that my thesis is really worth this prize. And unlike my peers who had the pleasure of standing here before me, my research is a little more directed towards the fundamental science direction. So it's really more about applying photonics for fundamental research. And as already mentioned, what we tried to do within the framework of my thesis was to combine integrated photonics with electron microscopy, and thereby trying to investigate new forms of light-matter interaction. Now, the interaction of light and matter lies at the very heart of many open scientific questions and also many technological applications. And one example for this, for example, is the area of quantum computation and quantum simulation, as illustrated here on the right with trapped ions. And many of these examples that one could think of really rely on a shaping of this interaction by gaining a degree of control over the optical state that we use to manipulate these systems. And this is basically facilitated by using integrated photonics. And this has already been demonstrated on various different matter systems, for example, again, the trapped ions, but also for other systems like atoms or quantum dots. For the interaction of free electrons with light, there has been various proposals for how to use this in a meaningful way. For example, in the generation of ultra-short electron pulses in the attosecond regime, enabling an investigation of dynamics in solids on an attosecond timescale, but also for using them in particle acceleration or in new versions of electron spectroscopy in quantum systems, and last but not least also for enhanced and aberration-corrected imaging in electron microscopy that really enables us to investigate not only solid-state samples but also biological samples on a nanometer length scale. So how can integrated photonics now really help us achieving this? Well, to this end, we first need to look at how can free electrons at all interact with light, because that's something that doesn't really happen in nature itself. So what we're considering is we're having an electron beam with a narrow energy distribution shown on the top right, and this now propagates by a sample. If the sample at the same time is illuminated with light from a laser, then what we can observe is that in the spectrum after the sample, we see pronounced sidebands that are formed, and these sidebands have a spacing to the initial peak and to each other of 1 photon energy. So what happens is that the electrons, when they propagate through this near field, are able to absorb or emit photons, so change their energy, and this is then also why we can, for example, then use this to generate short pulses, because parts of the electrons get accelerated, others get decelerated. And this interaction is typically very weak, so as we can see, the width of the spectrum is determined by the interaction strength, which in turn itself is proportional to the electric field strength that we apply with the laser. And this is the very problem of this kind of interaction, and that's also the reason why so far people really needed to use strong ultra-short optical pulses to modulate electron beams. And this is also exactly where our work tackled this field, mainly by trying to introduce integrated photonics resonators in the electron microscope, and thereby using that these resonators really allow for a strong resonant field enhancement, and at the same time also a so-called velocity phase matching. So we are able, by controlling the dispersion of the microring resonator, to make the electrons propagate with the same speed as the light that is going around in the circle. And this allows us to build up a strong interaction. And moreover, and this is just if you like, a small bonus, these structures are typically fiber coupled, so it's way more efficient to get the light inside the electron microscope than just trying to shoot a laser free space through a window into this tiny column. So placing these microring resonators that were fabricated by our colleagues in Lausanne in a group of Tobias Kippenberg, we are then able to observe for the first time a really strong interaction and efficient modulation of the electron beam for a low continuous wave optical power. And this is basically introducing a new and versatile platform for experiments on this electron-light interaction into our commercial electron microscope. Now this has a huge range of applications, ranging from very fundamental aspects like the quantum optics with free electrons, because this interaction itself can also be basically inverted. You don't have an optical field, but if your electron propagates by the ring, it can generate single photons or n photon states in a ring. This is kind of interesting, well, not only kind of interesting, but relevant maybe for quantum information processing. On the other hand, also, we can use this interaction to characterize the photonic structures that we put inside the microscope, and also learn something about, for example, the formation of nonlinear states like dissipative Kerr solitons in these rings. And last but not least, as I already mentioned in the beginning, this also introduces ways for novel electron spectroscopies and beam modulations. And this is, of course, work that would have not been possible without the help of others. And I'd like to basically thank not only my supervisor, Klaus Ropers, but also all the other people who assisted me, who supported me, who supervised me, ranging from Ofer Kwier and Hugo Laurence Martins, over my now colleagues Armin Feist and Germaine Arendt, and also our colleagues at the EPFL in Lausanne in the Kippenberg group. And I would also like to thank the Friedrich Ebert Stiftung for the funding of my master's studies, as well as the CRC 1456 and the Max Planck Institute in Göttingen for their funding of our work. Yes. And with that, I would like to thank you for your attention, and thank again the jury for considering me for this award. Thank you.
Thank you very much for your presentation, and congratulations on an awesome publication. And
So, Congratulations, and thank you for the presentation.
And now it is a bit sad, but also our pleasure to come to the last award of the evening, and for this year. There is also a special award of the Jury for Scientific Excellence for a postgraduate thesis, and this award goes to Dr. Daniel Werdehausen. His work is entitled Nanocomposites as Next-Generation Optical Materials, Fundamental Properties and Potential. The jury judges that Mr. Werdehausen's, theoretical penetration of nanocomposites addresses a very fundamental issue. The jury furthermore singles out 7 publications that feature Mr. Werdehausen as first author, as well as 3 patents, which demonstrate the close application of his research. Congratulations, and I really look forward to your presentation.
So sound check first. Okay, so yeah, thank you, of course, first of all, for the kind words. Yeah, my presentation today is going to be a bit less technical, actually, and I'm going to focus today on the question of actually why optical designers here often feel like they're shopping in an empty supermarket, and how optical nanocomposites can help to make them feel like Boris Yeltsin here, the first Russian president, when he walked into an American supermarket for the very first time. Okay, so first, let's focus here on the metaphor of the empty supermarket. And to do so, let's think of a normal optical material. Let's say this gray box here. And let's imagine this gray box here a conventional material, maybe a polymer. And then everybody in optics, of course, knows that this material has a certain refractive index, which for a fixed material is also fixed, and basically has a certain behavior over the wavelength. And then, in fact, when one is interested in this and one moves on to look at other polymers, or in fact also optical glasses, one sees that these materials have roughly and highly similar, actually, refractive index behavior. So the behaviors here of the refractive index are usually quantified in optical design in terms of its magnitude at the center wavelength, so sort of in the center of this curve here, and then in terms of its dispersion, so the wavelength difference. And the problem here is that we only have a really narrow range of optical properties available, whereas in optical design, so everybody in optical design, you can ask the people at the Fraunhofer Institute, you can ask the people, my colleagues over at SAIS, they'll tell you that having a wide range of properties available is a powerful tool in the design of high-performance systems, because you can leverage those wide properties to balance the different kinds of aberrations in optical systems. And this now is exactly where nanocomposites come in. So the quick idea behind nanocomposites is that we can actually put millions, billions, trillions actually of really tiny particles into, let's stick with the polymer, into this polymer as the host matrix. And this gives us new degrees of freedom, because we can actually, as we have just seen, tailor the concentration, we can tailor the materials of the nanoparticles, and we actually have to use a small enough size to avoid scattering. And this is exactly what I investigated in my thesis. So, and I'm just sticking to schematics today. So let's say we pick an ideally suited blue type of nanoparticles. So this would be, for example, diamond. And if we do this in the right way, we can actually then increase the magnitude of the refractive index here. So increase the magnitude without changing the dispersion at all. And then we end up with a material with a much higher refractive index. This is already a major benefit in optical design, because it, for example, allows us to correct spherical aberration. But the great thing now with nanocomposites is that we are not restricted to this blue type. Let's say we can also use a red type. And again, if we do this right, we can also use different concentrations of the two. And again, so just schematically, but you have two suited kinds of nanoparticles, and then we can do this in a way that we this time don't change the magnitude of the refractive index in the center, but rather just its dispersion. So we can see here that by now I'm basically, in the simulation, I'm increasing the concentration of the blue type of nanoparticle, and this increases the amount of dispersion. And such materials are actually really important in the design of basically polochromatic systems, of, for example, normal camera lenses, which have to work with white light. And this now is, for nanocomposites, why I use the metaphor of this really big American supermarket that has everything. Because we now actually see that we have a wide range of properties available that, in fact, by far, if you look at the data, exceeds those of normal materials. And in my thesis, I then moved on to sort of investigate the benefits for optical systems. And I actually today only have time for one really simple example. And I picked a simple example, basically one can think of, the example of just a positive lens. And we see here we have a positive lens, it has a certain focal length, a certain numerical aperture, and it's focusing the light down. But when we look more closely, we actually see that it's not doing a really good job, because it's not focusing the light down to a single point, but rather an extended area. So if we had a full imaging system with such a performance, its image would pretty much look quite blurry. So, and let's now investigate what this would look like with a high refractive index nanocomposite. And when we look at this layout here from a ray tracing calculation, we immediately see two benefits. So first, you can immediately see that the curvatures have decreased and the volume of the lens is much smaller. But secondly, and most importantly, we see that the spot size, the focus diameter D, has decreased drastically by more than a factor of 2. So this, an imaging system with such a performance, would lead to a much sharper image. Yes, I know with this image, I think the blurred version is actually better, but the optical quality is significantly improved, of course. So with this, I'm already at the end of my talk, so the only thing left for me to do is basically to extend my deepest gratitude to my collaboration partners, first and foremost, the people who supported me here in Jena, the EU for providing the funding for my work, and if you want to know more, you can check out my journal publications or the book I published with Springer last year. Thank you.
Thank you for the impressive and very graphic talk, literally. We're very happy to present you with the last award of the evening.
Yes, so congratulations.
Herzlichen Glückwunsch. And now, I think that was our last award. We don't have any left. I'll just say thank you so much for all these amazing presentations. I know you have a big future in front of each and every one of you. If you want to work in gravitational waves.
Or in photonics.
Or in photonics. Or in
Anyone
photonics.
else wants to pitch?
Back to you.
Thank you so much. And first, congratulations to all of you here in the front. And thank you so much, Robert Kamel and Michelle Hertz. And in case you're interested, I heard that the award is going to take place next year too. So everyone is happy for more applications. And that's where we come to the end of the day. For everyone remote, we have prepared a digital photonics escape room for you that you can enter. In the menu bar left, there is a section called Digital Escape Room or Escape Room. And you can just open that and we'll be guided there directly. It takes about an hour to play. Enjoy that. For everyone here on site, we have a barbecue outside. So when you leave the building, you will run right into it. And we see you tomorrow. And for everyone who is here, there is the industry breakfast at 8:30 a.m. in the opposite building in Fraunhofer IOF. You're all invited. Please be here. We're looking forward to see you at 8:30. And for everyone online, we start at 10 a.m. here and open the career fair for you. I wish you all a wonderful evening. Thank you for everyone who participated today in this first day of Photonics Day 2022. See you tomorrow.